Thus far this morning, we've heard from Christoph as to why the oceans, and particularly their chemistry, are of interest. We've heard from Louise, who, while dashing our hopes that the ocean is within a few meters of the surface, that is an important message, though, that if we want to get into the ocean, it's not going to be something that's easy. It's going to be a deep drill, a deep penetration. But there is also hope then that there are those sills, those subsurface lakes that are perhaps much closer to the surface, but even then we're not talking about a shallow penetration. But I will add something that what is still missing from that is that transport from the ocean through the ice crust to an area closer to the surface, whether it's a plume or a subsurface lake or extrusion onto the surface of Europa, what have you. There's still that transport that can alter that chemistry, that signal, that science that we're going after. And there's actually a workshop coming up in 2 or 3 weeks that is dedicated to transport mechanisms like that. But now we're taking a step beyond that and looking at more of the reality of what it's going to take to do something like this, to get access to the deep subsurface. And it's never going to be as easy as it is to do on Earth because we're talking about space missions, so the constraints are multiplied. So what Tom is going to do for us is give us a realistic idea of what it takes to not just get this deep access, but to get this deep access on another world, which has a whole raft of unique constraints that further complicate it. Thanks, Tom.
Thank you, Kurt. Thank you, Kurt. Thank you for also for spearheading this challenge here that we're going to get into, and also like to, I guess, compliment the organizing committee for picking the right week, because just had coffee this morning. I think I've realized that probably half the people in this room starting Wednesday are going to Antarctica for different experiments, and so we got everybody, a lot of really good people at the right time. A few years ago, I was asked to, at JPL, to sort of organize from a technology, advanced engineering, look into the future standpoint, what it takes to get to the water. So kind of a big, broad topic. And what do we need? What should we start thinking about today, as Kurt was saying, on the tall tent poles we should be working on today as we move forward over the years to really get the systems we need that are going to do what we talked about up front, and this dynamic, beautiful science that we're interested in. And the first thing you realize is that you stand on the shoulders of giants. The first project I worked on at JPL, the first flight project, was Cassini, building pieces of that, and then we saw just about a month ago when it finally ended, and it was amazing to see how the navigation and the trajectory folks now in 2017 were able to pinpoint, thread the needle through the gap and put it where it wanted to go. And when you were watching the feed when it went into Saturn, it was kind of amazing, because I think somebody actually said, oh, we were 18 seconds later than we expected loss of signal. I'm going, wow, you're sending something into this body out there, and you were accurate to 18 seconds in terms of navigation. We stand on the shoulders of giants because obviously, 15 years ago plus, after all the Galileo data, the Voyager data gave us that glimpse of what was going on, the Galileo data on all the imaging, that gravity, and understanding that there is potentially a big ocean under this ice sheet, work was done. It's really happy to see Lonnie Lane here, who was part of that early on. And when we started this project, the first thing we did was to call up a retiree, Wayne Zimmerman, sitting here in the front row, who built the Cryobot about 15 years ago and he took it up north to Svalbard, and in a flight form, not a flight system, but a form that with the power and could move forward. And so there's been a lot of work going on, and so what I want to summarize here is how that work came together, how we've done a lot of studies, small little pieces over the last few years, falling on that initial work, and then leading to a larger month-long a group of people getting together to summarize the needs. We heard about this already this morning. One of the things you realize is that this is a very easy project to communicate, outside of, us space nerds, technology people, whatever. My brother, a Chicago lawyer, when he says, what are you working out there in La La Land these days? And I tell him about, we're going to the water. Here's what we're doing. There's Europa and Jupiter. And, it's a half-hour conversation because when you, I'm sure, like everyone here, when you get on the airplanes and you actually tell people about this, it really captures the imagination, and it's a lot easier to talk about than some of the other technology things we work on, and I'm working on space computers and things like that. This chart here, Kevin Hand was good enough to send along, and his team from the lander studies and the science. And the important thing to note here is that we have this series, we're thinking about an exploration path, a true exploration path, as we saw earlier on with Clipper, hopefully launching in 2022. The team is working along. They are down into, moving into, phases of work at JPL and Flight Project Land. The study, again, a large group of people, at the concept phase, the lander, the Europa lander study, a large group of people are understanding what it takes to do that, at a depth of engineering knowledge to get to a science set of needs, which are really sort of growing in its breadth and its, number one, and its ability to actually, that we believe we could actually do this in the amount of time in this near future to get to the surface and then taste and sniff that surface. And then, starting to think about what are the paths down, maybe into the crevasses if they exist, and then into the ice. And here I'm going to focus all this on Europa. I think there's a lot that we've learned, I think, talking about Enceladus that will transfer pretty directly to Enceladus. And then, finally getting into the water, at least the ice-ocean interface, where we would have that first look into the water. And so, of course, it's all about the potential of life. The three big issues I always then, when people, say, well, geez, how can you actually believe that? And I go, well, it's more than belief, but it's not fact. But you better include the amount of time, these millions and hundreds of millions of years, where this has probably been sitting there and hard to comprehend. But of course, for us, it drives us. So, as I said, we came together. And we put together a lot of this work over the years, and we did a lot of studies on pieces. We're going to talk a lot about power. You got to think about autonomy if this is going to be sitting there in the ice for years, let alone the path to get there, the trajectory from Earth to Jupiter and Europa. And we all came together then for about 5 weeks this spring. And we brought all that together, brought the people together, and we ran one of these sessions. It was a 5-week session called Atelier, where you do a lot of interactive work with all the team together, and science through operations, and focus it and come up with not a design. So I'm not going to talk anything in here about a design, even though it would appear to be an instance of a design. But we wanted to do a trade space. We wanted to look at what are all the key issues, kind of trade them off literally over 5 weeks, and trade them off in a very organized manner, so that we understand what are some of the tall tent poles that we better be working on. And so we gave ourselves a very small goal here, and this was our organizing principle: from Europa orbit, deorbit, descend, and land, establish a surface system, travel through the ice, enter the ocean, and determine whether or not there is extant life. So we started, with the very biggest question. And so to organize that, we broke it into phases. To organize that top statement, we broke it into phases. And so this talk is going to go through the various phases and then the pieces that are necessary, sort of in a trade space from a technology-driven, forward-looking viewpoint of what we need to be working on. So the first phase is obviously the landing phase. So I'm going to tell you about how we're going to use a lot of engineering knowledge of the lander mission that tells you we're going to start with an SLS rocket, how much mass is on the ground, what it takes to get to Jupiter, what it takes to burn down into Europa, and get to the point where we're going to then go into a landing system in it, because that has to bound us on the amount of mass we could bring. Bottom line is, what can you bring? And then how you're going to fraction that out to some of the important things like power. So we have a landing phase. We're then going to go talk about, organize it into a surface phase, where the key points you want to work on, you have to release this probe. You're bringing a probe with you, an unknown probe yet. You're going to have to release it into the ice and all the issues of that. And then you're going to want to you're going to have to communicate back to Earth. That's the whole point. And then there's going to be trades between a direct to Earth or to the orbiter. There's going to be trades between communicating from the surface down into this probe, whether you're tethered or wireless. And then you have to maintain this operations in the radiation, obviously the massive radiation that you got to deal with there, and we'll talk a little bit about that. And then the big one, and I'll spend most of my time on for the purpose of this workshop to organize it, is the ice, what we're calling the ice mobility phase. And that is from the surface to the ocean, mobility to the ocean. You have to communicate to the surface, and then you have to have your science instrumentation along with you to perform the correct amount of science. And at this point we have sort of an idea of the science payload, just to give us some bounds again on mass and power and data rates. And some of the key things you're going to talk about are power and the communications in the ice, the electronics, and how they're going to manage themselves in the ice. Again, the instruments, and one of the things we talked about a lot was energy management. Was you're basically bringing an amount of energy to the surface, and how are you going to use? You have to, number one, bring enough to get you through some amount of ice, or else you failed in step 0. And how do you manage that energy in terms of watts per hour, in terms of power, to drive you through that ice in a manner that you could somehow today make a credible statement that you can make it happen. And then we're going to be in the water. We're going to have ocean access in a mobility phase where we actually enter into the ice, ocean interface, and then explore. And we thought about this. We want to explore the ice-water interface because we understand, of course, that that is where the aspects of life exist, at least as we know them on Earth. And then the last thing I have to talk about in here is the idea of planetary protection. And we take planetary protection very as an important ingredient to the whole development. It's not something that's a constraint from the outside that you have to work in or work around, but it better be built in completely. I was 1.5 years ago or so, 2 years now, I was at an NSF workshop, and I was really struck. I believe it was John giving a talk how on the Antarctic lakes, the small lakes up in Antarctica, to go through the ice there and get to the lakes that are on the rock ice interface, there's a planetary protection kind of equivalent requirement, and you better figure out and prove that what you're bringing down in your drilling satisfies the planetary protection for Antarctica and for life up there. And then I also learned about the Russians, who don't think about that, at least in the past, which was kind of fun. And I'm going to put a number up here of 10 kilometers just as a scale factor, as something we're going to base what we're working on. It's going to be sort of a baseline that we're going to work from, and I'll mention that. So, okay, so now let's get a little bit deeper. The trade space. So I mentioned we have a landing phase, surface and ice phases, and then the ocean phase. And again, for the purpose of this talk, I'm going to quickly, I'll have maybe one slide each on the landing and the ocean access. And so not to kill you or bore you with system engineering here, but we're going to break it up into, we broke it up into pieces, and then we had, basically, world-class teams come together to think about them over the short period of time using all our information. So we talked about the landing phase, and instead of entry, descent, and landing, when you don't have an atmosphere, entry, descent, and the entry into the atmosphere like on Mars, it's a deorbit phase where you have to burn yourself down so that you're falling, and then descent and landing. And there are methods to do that. There's a precision you have to worry about, and then the actual landing on the surface. You have to trade off and think about. On the other end of it, the ocean access, once again, we broke it into pieces, and I'll show you a chart at the end where we said nose in, look at this interface, and then look at going into the water some depth. But then where we spend most of the time, and I'll walk through these pieces, then you get to kind of the real deal stuff, okay? So how are you gonna go through this ice? And we'll talk about that. There's basically gonna be a mechanical and a thermal approach. We sort of looked at a lot of different approaches and moved them down into what we're gonna talk about: cutting, water jetting, and melting for various purposes. Power. Power is gonna be, if there's anything that drives you today, it's power. Very simple. If we're gonna start working on something today, let's work on power. Let's get our power, and it's gonna be all about power density, the amount of watt hours you could put into a volume. Okay, that's what's gonna get you, that's what's gonna make this thing work or not make this thing work. And so, you know, what method are you using and how you're packaging them up becomes very important, and then how you're converting thermal and electric, so you got the right balance between those, because it's all about this energy balance you want to think about. And then you're sitting in, you know, cryo ice on the top, you know, the 100 Kelvin, and water on the bottom, maybe, you know, 270 on the bottom. And so that's a gradient. In fact, that helps you in a certain way, we'll talk about. But then you can think about, you know, thermal control. It's really not a big driver here, but you better integrate that in with your power, passive and active versions of doing that. And then what I'm not going to talk enough about is autonomous navigation and operations. You're going to give you an idea that we could get to the water in 2 years, but you're going to take 2 years basically of autonomous operations. You're not going to be moving and phoning home and asking someone to go left or right a little bit if you could steer, et cetera. You're going to autonomously navigate, and then finally communications through that ice up to the surface, and where you're sitting in a radiation environment back home is essential. So ice descent. You know, fair amount of work, different pieces of work going on, both on earth ice, in the field, some tiny bit of cryo ice experiments. That is another area that we have to start really understanding with and without salts. And you break them up immediately, you see sort of in terms of a physics approach, there's melting, and there's kind of a melting approach and a mechanical cutting approach. They lead to different needs on your power system, how you travel, the equations that you would use to model those are different. So there's two sort of big branches of the tree up front, and how you're going to move through the ice. And the melting is simple. You know, you actually heat it at the tip, and you don't freeze along the way, and you move, and you hopefully keep moving. The goal is to keep moving. And
gravity.
Yeah, you're being pushed. You're melting below, and when the water will flow up behind you, and you keep pushing down. A lot of issues with that, obviously. And the power can be aboard the probe. You're going to bring it with you, or you're on the surface, and you have some big power source on the surface, and you tether it down to the probe. Trade-off. And then the rate of travel very simply depends on the amount of thermal energy you got, either on the surface or in the probe. Fundamentally, first order, where we're at today for this talk, at least, you know, double the amount of power, you're going to go twice as fast. Okay, and that's a big deal. And then, but then you start thinking about some other things you need, because melting is not enough. And the cryobot probe earlier on showed that water jetting can be very important. If you're melting this water, put some pumps in there. We think that technology, for the time we have for a space system, is feasible. And put water jetting in there so that it's sort of it's a less efficient approach than pure melting, because you're melting and then you're running a pump and you're pushing that hot water back down, but it helps you in other ways in moving the water around. And then a separate approach, mechanical cutting. Shaving, you know, if you're on ice, you don't drill or percuss, you actually cut along the grains, and you could create then bits for cutting, but that means you need the right amount of electrical energy, electrical power that you're going to probably derive from your thermal power. And then once you get cutting chips, you got to move them away from in front of you so you can keep moving. So all this comes big to understand what you could do. The 60s, the Filbert probe that kind of started the field. Almut, a modeler and a experimentalist, provided the first set of equations that basically are the fundamental equations used today to be able to understand how you travel through the ice. And what it's just telling you is that you need some amount of temperature, some amount of heat down here to melt what's in front of you. And then that temperature, the heat will flow up the wall, and it's going to be conductively move out into the ice. And if you're not going to be frozen in, you have to stay melting on top. You don't want to put too much into the ice, because then you're wasting energy. If you put too little, you freeze in, and so there's some happy medium in there. And so how do you distribute your heat, especially at the bottom, but then on the sides? And you form a little cavity, and you keep falling, ideally. So all of it is ideal. And so we have to worry about temperature versus depth. And as we heard this morning, one of the pieces you have to put into the models, very simply, are this model, is what is the temperature profile as you go down? Again, 100 to 270, and depending on sensitivities of temperature. And then the other big driver is the amount of salt, which drives your conductivity and your specific heat in these models.
Tom?
Yeah.
Does that mean keeping the column above the probe liquid for 30 kilometers?
No, it will refreeze behind you. And so if you have a tether, for example, you have to bring it with you and put it and drop it out behind you. But it will refreeze behind you without a doubt. Another big deal is the sublimation. At the surface, you had vacuum and ice. You're not in ice. You don't have that pressure there, and so you have to think about sublimation. The model doesn't include that, and some viscosity. Your friction at the walls. But so it's a very simplified model, but it gets you going, and it has some experimental validation. So if you put that all together, like I said, a lot of teams come together. This model, we were able to work with Bill Stone and his crew at Aerospace, among a lot of other folks. And so here's sort of the numbers that we think about. So what we're showing here is, and so what matters is the diameter of the probe, the length of the probe, and the amount of power you put in, just to really get it down to, 0th order here. And so, you do a lot of trade studies around that. And if you pick that you have 7.5 kilowatts of thermal power, and then you just say, well, okay, we're going to take 85% of that. And we pick, and you run, and you look. We looked at a probe here, which was 16 centimeters by about 2.5 meters. And we look at then, that model will tell you the rate of travel, meters per hour. So a number of about 1 meter per hour, 3/4 or so, is a really good number to keep in your head if you're traveling at that rate. And then here is the depth then versus the time in days to travel that distance. And again, we picked a baseline of 10 kilometers, not because we know it's 10 kilometers, and we saw numbers today could be 20 or 30, perhaps it's even 5, but so we picked a baseline of 10 kilometers, and of course the models will run past that. But if you pick, perfect ice, for example, on here, you're within a year to 2 years, and if you have a lot of ice in there, which really improves the ability to melt, transfer the heat, you even get smaller. And so there's a lot of there's a range of variability on the models. We're starting some work up with not only these sort of AMAT models, which are first order but very good physics-based models, but in finite element models of actually a structure with a temperature variation along the probe, and ice variance along the way, and rates of travel, and then you want to be able to put salt content, you want to put cracks in there, and so on. And so a true physics-based model, and we've been doing some work in getting that going for these type of probes. So we talked about other pieces, water jetting and cutting. I just want to include in there. Basically, if you're going to have sediment, this icing, perfect. You're going to have all sorts of stuff in there, and if you just melt it, you might just stop. Because you can't transfer the heat anymore because of sediments or whatnot. And so I mentioned the water cutting we could put in there. Water jetting, think of just 3 jacuzzi jets that are pushing forward, and then as well as a motorized blade with a cutting tip, and manage your power correctly. The big deal, heat and electric source. So then we walked through and said, well, what do we got? We got nuclear, meaning in this case, we'll get to radioisotope thermal. It would be wonderful to have a reactor sitting there and forget about 7 kilowatts, but talk about 700 kilowatts. In today's world, in the time frame we'd like to get to, perhaps a stretch. Stored energy, basically, you lose it right away. You just can't store enough energy carry it with you the years you need to get to Jupiter, and then the couple years or so or more that you need to get underground. GPHS, workhorse we have today for, since the Voyager days. These blocks of a marshmallow of plutonium dioxide giving off 250 watts or so of heat continuously, 87-year half-life, boxed into this 10 by 10 or so by 5+ centimeters safety, basically a safety device so that we're safe with using it. And for example, you could use the GPHS blocks. We've also been talking to people in the DOE who have research going on in using this exact same plutonium dioxide, but packaging it a different way. As I said, it's not only the amount of plutonium dioxide for this heat that you would bring along, but if you got to package it into these big blocks for safety reasons, which of course you have to do, are there other packaging approaches? And there are potentials out there today that are being worked on. More quickly now, probe thermal configuration. If you got that heat, now I'm starting to show you sort of don't think about this as a design at all, but think about this as an instance of what's possible. You have a probe, and what you have to do is control the temperature around that probe. So if you got a big blotch of power sitting there, say this plutonium dioxide, whether it be our general purpose heat sources, the GPHS, or some newer variant, you got to take that heat and put it in the right place so that you melt appropriately. The massive amount has to be at the nose so that you travel, but then put some on the side. Communications, next deal. What's very interesting, and the teams, from 15+ years ago, 20 years ago, looked into this, and what's great is that in really rock solid 100 Kelvin ice, electromagnetic, relatively low frequency, 100 megahertz, travels really well. You get little loss. As it gets warmer and gets wetter, you get higher attenuation. So a design had been put together with pucks to actually drop pucks away in a leapfrog manner to get your comm back to Earth. You could also bring a tether. And so at the end of the day, we want to have a tether and pucks. We want to do RF and, if we can, acoustic. Acoustic transmission is not out of the realm. It's really a size issue. We do it today so that you have this functional redundancy that we like to think about, as well as with the melting and cutting and water jetting up front.
Can you talk more about this acoustic?
I'm sorry?
Could you talk a little more about the acoustic communication? I mean, how would that work when you have potential fracturing processes going on?
Correct.
Making their own acoustic?
So we have not dug too deep into that. You would want it for more of, if it does work, you want it more, and you can make it small enough and enough power as sort of a backup approach, as an additional communications where your baseline is going to be RF. We believe the acoustic signals, they do go through the water, so we're thinking about when you get down more towards where it's warm ice, where the RF has problems, the acoustic might be better down in the water, obviously, and then in the warm ice above the ocean is where it would really come into play rather than the top.
Sorry, really quick, maybe I missed this at the beginning.
Sure.
Are you envisioning that there's some kind of lander that's sort of the home base? And then
Yeah, that'll come into the next one.
so it's
Yeah.
communicating with the lander at one end.
This is all coming up to the lander that goes back to Earth. Yes. Here's a little picture on that. We'll get more, but if we did have an orbiter, we ran the numbers of the communication systems. 2 meters on board an orbiter with 100 watts at X-band will get us to the surface at the data rates of this science instrument set that we said we have the amount of capacity of bytes we want to bring up through the surface. We could store and forward along our pucks, get them up to the surface, and then burst them up to our, whether it be an orbiter or direct to Earth. Direct to Earth really cuts down the amount of data you could bring back, but it's feasible. A lander configuration, this is the lander that you just asked about, and a relatively modest antenna sitting on the surface with a relatively modest amount of power to be able to talk up to the orbiter in this case. And then in a surprising manner, 5 of these communication pucks is reasonable for our baseline of 10 kilometers. At 100 megahertz, putting the data that we think we need on there.
Are those batteries or RTGs?
So yeah, on the pucks is again another small RHU, RT, radioisotope power source, but a small one just to give you enough power for the puck. And they exist today to a degree, and maybe a slight change is needed for the puck. We won't be able to spend enough time on this. It's something we're going to have to learn about as we go on, how to operate a vehicle in this kind of environment, you know, autonomously, both through the ice descent stage, communicating the science. So we talked with various science teams on, you know, how much science do you want to learn going through the ice? Of course, an infinite amount, but we want to get to the water and not, you know, not slow yourself down, and so on. And so communications on what you can actually do in the ice, given the science data, releasing these pucks, and then allowing them to freeze in behind you. You're always freezing in behind you. And then I won't talk about it all, but navigating radar and sonar through the ice. I know there's some work going on, WHOI and otherwise, that understand how to, in water at least, and in ice, on how deep radar or sonar will go so that you can move yourself a little bit. We think about over 100 meters, you can go 6 degrees and navigate yourself by either differential heating your probe tip, or this water jetting with your 3 jets. Surface, here's the surface-based functions, just one slide now up front. What's the big deal there? You land, and the biggest one is the startup phase. And so the ideas that we worked out and modeled were to put a cap down. You're in vacuum, you got ice. Melting is going to be very difficult because you're sublimating. If you put a cap down and start cutting and water jetting and melting, you could build up pressure if you can get this cap to seal. And in fact, it doesn't take a relatively long amount of time to build up enough pressure so that the melting starts taking over the triple point changes from the sublimation. The other big deal is the radiation. And so it became very obvious at some point that once you're down couple meters, you're at least on 5 of your 6 sides, while 6, once you melt in, you're protected by the ice. So you would take your critical electronics, melt them down with you, hopefully a very small package, and then you'd have a probe up to the surface to your antenna, and ideally on the surface there's probably some power that we have to figure out, and an antenna on the surface for communication. And then the comm that we talked about, either direct to Earth or through a relay. So this initial phase, now we're magically going to land. We're going to install this cap at the surface, and we're going to start melting, cutting. Probably this is where the cutting and the melting become very important for the sublimation problem. And then drop your electronics package into the ice, and then move forward. What I call the DDL phase, because we have so much knowledge now in terms of mission design. So I get Michelle, my Michelle, 5 minutes do I got in red? Okay, she ran away from me already. Okay.
No, you'll take 5.
Thank you. Oh, there you are. And there's a big deal because there's a lot of technology that's been going on in terrain relative navigation and hazard avoidance. And so in Mars 2020 is going to first demo it, hopefully with the Europa lander concept mission, would use this completely to land. Now we're landing in a football field, precision powered landing in a football field rather than a 10-kilometer ellipse, like you think back to Curiosity, where you have some probability of landing in a 10-kilometer ellipse. We're going to have powered landing down to a football field, 100 meters is the goal here, which obviously for European surfaces, as we saw from Louise earlier, you know, you want to be able to find a football field size safe landing spot, and that's sort of a driver. We're in the water again here. This, you know, theoretically here, because we want to put a whole package together. Remember, this is not a design again. But we said, okay, we have to put time around this and put volume and mass and powers. And so we walked through with, let's do 4 segments. Nose in. So probe nose in. We got down and we realized, you know, magically we're at this, hopefully we're at an ice-water interface. It's not going to look like that at all, but we're at a ice-water interface. And the first thing we want to do in terms of a kind of a ConOps to think about it, analogy by, is sort of anchor yourself and poke your nose in the water, you know, turn on your LEDs, your cameras, start sampling to water. This is, you know, the first reason why we went there. Once you're comfortable there, then the idea was that you would actually tether yourself, and part of the probe in our design, our instance of a design, actually releases off, so that this probe now is fully submerged into the water to get us going, and then we learn how to do some operations at that point, and then ideally you have an underwater vehicle, perhaps a buoyant vehicle that will pop out and will run along that surface, probably tethered, perhaps to some radius, so that you're examining the point around you. And then you could envision at the end where you could cut that tether and let it fall, taking measurements along the way until you run out of communication. So design assumptions. So what we worked from the beginning is, again, we said we're gonna start from the mass that's available for an SOS launch. We're gonna use everything that's been done to the point you're deorbiting, and we're gonna bring the same mass then to the surface that an engineering team is working on for the lander, and that's about 1,000 kilograms, which includes this big engine to slow you down so you can start falling. But then the lander system is considering probably a sky crane system, modified version of the Mars systems. But that throws away a lot of mass, which we said is not appropriate for what we want to do. We want to land all the mass and use all the mass. So we don't use a sky crane, it's a powered landing, TRN with the train relative nav. And so then we said, okay, we're going to start from power sources we have today, or modified from today, and that leads you to the radioisotope for the years that we want to be in action. And obviously, what advances can we make? We took that 10-kilometer baseline with the temperature profile and the salt content that as we understand it today. And then we said in practice, the whole thing, we're going to put 2 years around this, back to our initial time of travel equations. It's 2 years through the ice. And we don't want it to be 5. It's not probably even feasible to do half a year or 1 year. 2 years became the sweet spot. Have a conceptual design, just to put your head around something. It's not infeasible to think about a 2 meter by about a 23, 24 centimeter diameter vehicle. It runs about 200 kilograms. If you took that 7 kilowatts of power system, which today does not exist, in that form factor, we would need about less than 10% of that in electrical power to do your drills. It's dominantly you're drilling water jetting down there, you're cutting water jetting, the amount of power. And as you break it up, that yellow cylinder on top, the blues are the pucks, the yellow cylinders is the science package, maybe the underwater vehicle. Green is electronics. We have a power system in there of this. If we use this, if we were able to develop these plutonium dioxide pellets and package them up, and then your whole kind of front face of the drilling and cutting up front. We did come up with we said, okay, well, let's say we weren't, in our trade space, we went off on a lot of different angles and said, well, what if we use the GPHS blocks? Well, it runs off to about 4 meters over, same diameter, but about 4 meters, which makes a big difference in terms of rate of travel and so on. And actually, how you move that heat around becomes different. And so, you could think about either approach. In this, the numbers are for the top approach. So
let's move ahead beyond the point design and wrap it up.
Yeah, I got just two charts here. So looking ahead, what do we know? And so as mentioned, what are we going to know? We heard this earlier on Clipper. In terms of a landed operation, the radar, the surface mapping, and the thermal mapping, and imaging spectroscopy from Clipper are going to give us an enormous amount of information about the surface. Then a lander concept would, if available, will tell us that we can land to 100-meter accuracy. We would get all sorts of descent and surface imaging through that process. And then, of course, we would learn all about the surface operations. We went there, including the salts and so forth, at least on the surface, and hopefully the seismometer array of sensing. So I just want to close with that. This is putting a big picture together. Think of this as just a trade space of these are the technologies that are needed, but you need to bound them by what's reasonable and feasible when you get on the ground on Earth and think about all the way through operations. That was the point of putting the pieces together. And so those are the tall tent poles as we envision them. Thank you very much.